We're now going to look at the final topic of this class, and that's Markov process. So a couple definitions here. At each trial or iteration, a Markov process will involve n possible states. So you're going to see this word thrown around a lot, and this is everything that you can end up in. So all the different states that you could be in. The transition probabilities are the probabilities going from one state to another. And the notation that we're going to use is P sub I j. And this is going to be the probability of going from state I to state j. The example that we're going to look at is we're going to suppose there are two grocery stores in a town. There's Murphy's and there's Ashley's. Customers are going to be making weekly shopping trips. A person will continue to shop at Murphy's 90% of the time. So just from this second kind of bullet point here, the probability, and we haven't numbered them yet, but we're going to number Murphy's as number 1. The probability of going to Murphy's and staying at Murphy's is 0.9. A person will continue to shop at Ashley's 80% of the time. So we're going to call Ashley's second. So the probability of going from Ashley's and staying at Ashley's would be 0.8. The trials here are the shopping trips, and the different states that you could be in are the different grocery stores. What we want to do is we want to make a transition matrix. So the transition matrix is you're going to put all the different probabilities into a matrix. And we can call it T for transition if we want. So a transition matrix is going to have the probability of going from state 1 and staying in state 1, probability of going from state 1 to state 2, the probability of state 2 to state 1, and probability of 2 to 2. So if you go back to the basics of the matrix video that I just did, you should know what these subscripts are. So that P11 is row 1, column 1, P12, row 2, column 2. From our problem, we know that P11 was 0.9, and I know that P22 was 0.8. The question is, what is P12 and what is P21? Well, if the probability of staying at Murphy's was 90%, that means that the probability of leaving had to be 10%. So P12 is 10%. And then the probability of staying at Ashley's was 80%, so the probability of switching would be 20%. So our transition matrix is going to be 0.9, so that was P11, 0.1, that was P12. Next we need P21, so that was 0.2, and P22, which is 0.8. So there's our transition matrix. The question that we need to answer, and this is the whole Markov process, is what happens in the long run? So what can this business expect to happen in a few years from now? So the way we're going to set this up is we're going to have pi sub I n. This is going to be the probability that a system is in state I after n trials. So for this, maybe the company wants to know 6 months from now, what's the probability that people who started shopping at Murphy's are still shopping at Murphy's? Then that would be something like pi 1 of 26. That would be saying, what's the probability that people are shopping at Murphy's after 26 trials? Remember that each trial is a week. Then we're going to label capital Pi is our steady state matrix. And it's going to be pi 1 and pi 2. So pi is your steady state matrix. This capital pi, what's important to note about that is once you reach this capital pi, you're not going to alter the behavior. Once you reach this steady state, everything is going to remain the same. What we want to solve, so we need to figure out this pi, that's the goal. Pi here is the ultimate goal, figure that out, is we need to solve for pi using the equation pi equals pi times our transition matrix. And the reason this is going to solve our equation is because doing the transition matrix to this matrix pi doesn't do anything. Right? This is like saying pi times my identity is exactly the same as pi times my transition matrix. So we're trying to solve for pi using the formula that pi equals pi times my transition matrix. So we're going to solve our system. Our system had two states, right? So our system, the steady state matrix is going to be pi 1 and pi 2. And our transition matrix, let's not forget that, that was 0.9, 0.1, 0.2, and 0.8. So we are trying to solve the equation pi equals pi times the transition matrix. So let's go ahead and substitute all of those in. So pi 1, pi 2 equals pi 1, pi 2 times that transition matrix. So 0.9, 0.1, 0.2, 0.8. What I'm going to do is I'm going to subtract everything that's on the right-hand side over to the left. And that's going to leave me with nothing on the right, but that's okay. So I'm going to subtract everything over and I'll get pi 1, pi 2. Remember, that's what we're trying to figure out. Minus pi 1, pi 2 times that transition matrix. And now the whole thing is equal to 0. Next, what I'm going to do is both of these terms have that pi 1, pi 2 matrix in it, so I'm going to factor it out. So I get pi 1, pi 2, and now I'm going to factor it out. Well, if I factor it out of this first one, it's kind of got this squiggly line underneath it. That's kind of like factoring out and just having 1 left over, but we don't have 1, we have an identity. So I'll write my identity matrix. And then minus my transition matrix. So again, what I did between this step to here is I factored out that steady state matrix from both terms. Factoring it out of my first term left me with the identity. Factoring it out of the second term left me with the transition matrix. Next thing I'm going to do is I'm going to actually subtract these two matrices, and you just do that component-wise. So for this first one, I'll do 1 minus 0.9, which was 0.1. Then I'll have 0 minus 0.1, so negative 0.1. Then 0 minus 0.2, which is negative 0.2. And 1 minus 0.8, which is positive 0.2. Now we're getting somewhere. Once I get to this step, I'm actually going to multiply these two matrices out. And again, I know they equal 0. So if I multiply those two matrices out, that's going to result in, let's see, this was a 1 by 2, this was a 2 by 2, so it's going to result in a 1 by 2 matrix. For my first one, I'm multiplying the first row by the first column, so it looks like 0.1 pi 1 minus 0.2 pi 2. Again, that was the first row, first column. For my second piece, I'm going to have negative 0.1 pi 1 plus 0.2 pi 2. So both of my components are written there. I know that it has to equal 0, so both of those are going to be equal to 0. So I'll have 0.1 pi 1 minus 0.2 pi 2 equals 0, and then negative 0.1 pi 1 plus 0.2 pi 2 equals 0. Now, I don't know if you notice anything about these two equations, but if you look at them, they're the same equation. It's just one has been multiplied by a negative. So because of that, we really only have one equation from this. The other equation that we're going to use is that, remember, pi 1 and pi 2, those are probabilities, and probabilities have to add up to 1. So my other equation is pi 1 plus pi 2 has to equal 1. Now that we've actually multiplied it out, we did get a system of equations. Our system was 0.1 pi 1 minus 0.2 pi 2 equals 0, and then also pi 1 plus pi 2 equals 1. So we are going to solve this for pi 1 and pi 2. And there's a couple ways you could do this. It's kind of up to you. I would probably take this first equation and solve it for pi 1. So I'll do 0.1 pi 1, add that other one to the other side, and then divide both sides by 0.1. So pi 1 equals 2 pi 2. Then I'll take that and plug it into my other equation. So 2 pi 2 plus pi 2 equals 1, which means that 3 pi 2 equals 1. So pi 2 equals 1/3. And I know from this equation that pi 1 is just 2 times that value. So pi 1 is 2/3, pi 2 is 1/3. And what that means for us is that in the long run, we can expect 2/3 of customers to be shopping at Murphy's, and we can expect 1/3 of customers to be shopping at Ashley's. These are the steady states for the two states. So state 1 was Murphy's, state 2 was Ashley's. This is what we expect in the long run. Let's change this problem slightly. Let's find a new transition matrix. What if I, instead of having the 0.8 and everything like that, what if I change this to be 0.85, 0.15, 0.2, and 0.8? So how would the long-term probabilities change if I changed the 90% to an 85%? And we're going to go through the same thing. We're still going to have that steady state matrix, which was pi 1, pi 2, and I want to solve for this pi 1 and pi 2. So the way I'm going to do that is, again, we're solving the equation pi equals pi times t, and we did a bunch of steps, and we eventually got this down to pi times I minus t equals 0. So if I were you, I would start at that, because it's going to be the same every time. So pi times I minus t equals 0. So pi 1, pi 2 times, and let's see, what is I minus t? Keep in mind that I is your identity. So if I do I minus t, it looks like I get 0.15, negative 0.15, negative 0.2, and 0.2. Then we'll go ahead and actually multiply this out on the left. If I multiply this out on the left, I get 0.15 pi 1 minus 0.2 pi, and this should be a 2 here, pi 2 equals 0. And then negative 0.15 pi 1 plus 0.2 pi 2. And both of those, there's the same equation, so I can just get rid of one. One's just been multiplied by a negative, so I'll get rid of this one. The other equation we're going to use is that pi 1 plus pi 2 equals 1. So do the same process as before. I'll solve this first one for pi 1. So 0.15 pi 1 equals 0.2 pi 2. Divide both sides by that 0.15, and I got 4/3 pi 2. I'll take this and plug it in here. So 4/3 pi 2 plus pi 2 equals 1, which gives me 7/3 pi 2 is 1. So pi 2 is 1 divided by that 7/3, which I got to be about 0.4286, which means my pi 1 is 0.5714. So now, if we just change that one probability, in the long run, about 57% of shoppers will remain at Murphy's and about 43% will go to Ashley's. That's what these two are. So pi 1 was the probability of staying at state 1, pi 2 probability of staying in state 2, and they're getting closer to 50-50 just by changing that one probability.